In this video, we'll be looking at the different reactions that alcohols can undergo. But before we jump into the reactions, we have to take a look at the classifications of alcohols because this does matter to tell what type of reaction will happen with them or what they will change into. So alcohols can be classified based on being primary, secondary, or tertiary, similar to how the amines are classified. So if we look, the first one here, propan-1-ol, is a primary carbon. Now the reason it's primary, here's our alcohol group. The carbon it is attached to is only attached to one other carbon. Okay, that's what makes it a primary alcohol. A secondary alcohol, look at our alcohol group. The carbon that's attached to is attached to two other carbons, making it secondary. And finally, we have the tertiary, where our alcohol, the carbon it's attached to, is attached to one, two, three other carbons, making it tertiary. So we can classify alcohols as primary, secondary, or tertiary alcohols. Okay, and this will become important when we take a look at the second reaction, which is oxidation of alcohols. The first reaction is that alcohols can combust. So they are actually used as fuels. They can combust, same type of reaction we saw when the alkanes combust, except alcohols combust much more readily than their equivalent alkane because they're already partially oxidized. So they have some oxygen on them already, but this means that they do release less energy than their equivalent alkane would. Okay, so we have our alcohol plus oxygen goes to carbon dioxide and water, or if you remember, if it was incomplete combustion, if we had a lack of oxygen, it would go to carbon monoxide. Okay, alcohols are used as fuels. So you can use alcohols as pure fuels, like methanol is used as a fuel in competitive motorsports. So in dragsters and monster trucks, you use a high concentration of methanol. Um, or it can be blended with regular petrol or regular gasoline. So if you go to the gas station, you'll actually see there's a little sticker usually on the pumps and it'll say may contain up to 10% ethanol. This is often included as like a cleaning agent, but it also combusts as well. Now, here's a question to think about. I'm not going to state an answer to this, but much of the fuel or of a fuel ethanol is made from fermented crops. Okay, and these crops, if we weren't using all of this ethanol and fuel, these crops could be eaten. So the fact that we do use it as fuel drives up the price of these crops to be used as food. And the question is this an acceptable practice? So again, I'm not giving an answer, but this is just something to think about and discuss on your own time. Okay, so that's reaction one, combustion. The next reaction we have is the oxidation of alcohols. So alcohols can be oxidized. So we're adding oxygen to them. This is the classical definition of oxidation, is the addition of oxygen. So they can be add oxygen to turn alcohols into aldehydes, ketones, and carboxylic acids. What they turn into depends on if we're dealing with a primary or secondary alcohol. Okay, the oxidizing agents, we need something with a lot of oxygen to give that oxygen to the alcohol. So the oxidizing agent we use is potassium dichromate, K2Cr2O7. So we have 7 oxygens. There's a lot of oxygen there to supply as an oxidizer. And we have to acidify this, though, with sulfuric acid. In this process, when we oxidize the alcohols, the chromium, it starts as an orange color, so potassium dichromate is orange, and after it loses some oxygen and oxidizes the alcohols, it itself becomes reduced and it changes to a green color. And this is actually the reaction that would undergo in, say, the breathalyzer test, right, to test for the presence of alcohol. So you'd see this change in color from be able to detect from an orange to a green. So let's start with a primary alcohol. We take our primary alcohol, we add an oxidizer. So this O, there's other things besides potassium dichromate that can be used as an oxidizer. So we can just use this O as a general symbol for the oxidizer that's being added. So we add this, we add our sulfuric acid catalyst, and we oxidize this alcohol. So the same position, if we look at the carbon, if we number these, carbon 1, 2, 3, the aldehyde is still in the same position. And what we've lost here in the process is 2 hydrogens. So we've lost a hydrogen off of our carbon 1 and a hydrogen from our alcohol here and created an aldehyde. Okay, in order to produce this and to get the aldehyde, we have to do it through distillation. So what distillation is, this is what a distillation setup looks like. I believe we've looked at one of these before in the class. So we take our sample of alcohol, which goes in the flask here, and we put all of our reactants, all of our reagents into this flask. So our alcohol, our potassium dichromate, and our sulfuric acid, and we heat it. Okay, the thermometer there is to test the temperature. So based on the boiling point of different substances that we're looking for, we can tell what substance is being boiled based off of the temperature on the reading of the thermometer. So we heat it up. The potassium dichromate is not going to boil out. Any water in here is not going to boil out. So the aldehyde boils at quite a low temperature, usually 30 to 40 for some small chain aldehydes. Okay, so it'll boil out and travel up through the tube and head down this way. Now this is what we call a condenser. Okay, the condenser has a tube in the center and water runs around the outside. So you put the water in the bottom, it fills it up, and it flows out of the top. What this does is it takes our gaseous aldehyde and turns it into a liquid. Okay, and the liquid goes through and then drips down into a collecting flask. Okay, and we call what comes out of it the distillate. So this is how we can separate the aldehydes. So we have our mixture here of our oxidizer, our catalyst, and all that stuff. We just want the pure aldehyde. So again, we distill it, and we gather the pure aldehyde in the end. We can then take that aldehyde and add, if we wanted to, we could add more potassium dichromate and more acid catalyst, and turn that aldehyde into a carboxylic acid. Or you can also go directly from an alcohol to a carboxylic acid. So this is the next step. Again, we're still looking at the same carbon, but we've removed this hydrogen and replaced it with an OH. So we've added more oxygen to our alcohol. This happens under reflux, okay, is the condition. So we still need our oxidizer. We still, in both of these cases, need our H2SO4 catalyst to acidify our oxidizer. But the difference is distill if we want the pure aldehyde, reflux if we want to go from either the alcohol and the aldehyde to the carboxylic acid. So what reflux is, similar. What reflux allows us to do, though, we have our condenser again, just like we did in the distillation tube. So we have the water coming in and the water going out, and we have a tube in the center here. Okay, that's open at the top. So to turn the alcohol into a carboxylic acid requires quite a bit of heat. In fact, it requires the temperature to be higher than the boiling point of the alcohol. So our mixture in here, the alcohol is actually going to start to boil. So what happens is the alcohol goes up. In order to maintain these temperatures, we attach a condenser. So the alcohol goes up as a gas, condenses back into a liquid, and drips back into our reaction mixture. So the reflux allows us to boil or react compounds above their natural boiling point by causing them to condense so they don't escape the system. So again, primary alcohol can be oxidized into an aldehyde, or it can be oxidized into a carboxylic acid. Secondary alcohols, okay, we're not on the end of a chain here, so we're not going to get our carboxylic acid. Secondary alcohols, we use the same conditions. Okay, we use our oxidizer, our H2SO4, and we're going to distill just like we did with the aldehyde. Okay, so secondary alcohols will react to a ketone. So it creates that double bonded oxygen just like the aldehyde, but it's in the center of the chain. If we add more oxidizer to the ketone, we get no reaction occurring. Okay, it can't be oxidized any further because we're not going to break the carbon-carbon bonds. And Lastly, we have the tertiary alcohols. So the tertiary alcohols, there's actually, we can't break these carbon-carbon bonds. So we can't actually do anything with a tertiary alcohol. You can add the oxidizer and the catalyst, but no reaction will ever happen. So this is how we can actually distinguish if we have a mixture of alcohols and we want to know which one, if we have primary, if we have secondary or tertiary. By oxidizing it, you can actually distinguish, because tertiary, no reaction will happen, which means the oxidizer will stay its orange color. Primary or secondary will both oxidize, and the oxidizer will change from orange to green. Okay, so this is a summary here on this page of all of the different alcohol oxidation reactions, so primary, secondary, and tertiary. And there's one more alcohol reaction we're going to look at, and that is esterification, which we also is also known as condensation. So in an esterification reaction, we are, what it says up at the top, we're creating an ester. Okay, so this reaction involves a carboxylic acid and a alcohol adding together. We use an acid catalyst, so again, we can use sulfuric acid. And we use some heat, so we don't need any other special ingredients or anything, just an acid catalyst and heat. And this produces an ester. So we see that the methanol here gets added on to the other side of the oxygen. So essentially what's happening is the alcohol on the propanoic acid is getting replaced by the methanol. Okay, in the process, we have an OH and an H, which are released as water. Okay, this is why we call it a condensation reaction, because as this reaction proceeds, you'll see water forming on the flask. Okay, so again, our carboxylic acid plus an alcohol goes to our ester. And you'll notice the name. So the name of the carboxylic acid, regardless of the size of the chain, will always give you the root name of the ester. So here we have propanoic acid. We change it to propanoate, and we add whatever the alcohol is gets added as the branching group on the front, as the prefix. So again, it doesn't matter. If we switch these, if we had methanoic acid with propanol, then we would create propyl methanoate. Okay, so the carboxylic acid always becomes the root word of the ester with O8 at the end. One neat thing about esters is they're quite volatile, so they have quite low boiling points, and they actually have very pungent smells to them. All esters have very distinct smells. One example is 3-methylbutyl ethanoate. Okay, and that's actually what gives bananas and pears their smell. So kind of an interesting little feature about them there due to their low boiling point. They don't have hydrogen bonding. And that brings us to the end of our alcohol reactions.